And remember, extrema is just a fancy word for minimums and maximums. So what we want to do is find all the local mins and all the local maxes. We just want to know where they occur. So generally, or typically, you might be asked to find out, what the actual mins and maxes are. So you might want to give both the x and the y value. But what we're doing the second derivative test here, what's really different is just how we find the x value. But if you want to find the y value, that's just going to be the same thing. Once you get the x value, plug it back into the original function to get your y value. So, we mainly right now just want to highlight the differences between the second derivative test and first derivative test, and the only difference is in finding the x value, or in other words, where the local extrema occurs. But finding the y value is exactly the same. Once you have the x, just plug it back into the original function. But anyway, let's do an example real quick. So let's say part A, let's say we have f of x equals x squared. Okay, so what we do, whether we're doing the first or the second derivative test, the first thing we want to do here is take a derivative. Okay, so what is f prime of x? F prime of x is 2x, right? All right, now we want to find the critical points. So to find the critical points, we set this guy equal to 0. Okay, so 2x equals 0. What does that mean? That means x has to be 0. Okay. So this is our only critical point, x equals 0. All right. Now we have to be careful here because when we do the second derivative test, we want to make sure that f prime to c and f double prime to c both exist. Now, f of x is a polynomial, so all of its derivatives are polynomial, so we don't have to worry about anything like that. And we found this by setting the first derivative equal to 0. So for this simple example, we don't have to worry about anything not existing. I just want to point that out. Just make sure that you look out for that. And actually, for the rest of this video, we're not going to have to worry about that. But for the more complicated examples later on, we will. But anyway, so x equals 0 is our critical point. So now let's see, what's f double prime of x? F double prime of x is 2. Okay. So f of x is x squared, f prime of x is 2x, so the second derivative is going to be the derivative of this, which is just 2. Okay. So now Now the way we do this second derivative test here is we evaluate the second derivative at this point x equals c. So this is our c right here. Okay. Now we're going to do the second derivative test where 0 is our c value. Okay, our value of c here. Now the second derivative is actually just a constant, so it's always 2 no matter what x is. So it's almost kind of trivial in a way. But anyway, what's happening here is f double prime of c. Well, what's our c? Our c is 0. Okay, so f double prime of c, which is f double prime of 0, that's 2. Okay, because no matter what x is, that's always 2. So is that positive? Is it negative? It's positive, right? So from the second derivative test, what can we say? We know that f of x has a local min at x equals 0. Okay, so that's what we just found that out from the second derivative test. Okay. So if x equals c is a critical point of f of x, and if f prime to c and f double prime to c both exist, then this first case is what applied here. Okay? So we had our function f of x, x squared, take a derivative, find all the critical points. There's only one critical point, so now we just find the second derivative, evaluate it at that critical point, okay? And we end up with f double prime of 0 is 2, which is positive. Okay? So just right away from the second derivative test, that tells us f of x has a local min at x equals 0. Okay? And we know x squared, if we were to graph that, it's just a simple parabola, right? So if we were to graph that real quick, what's that going to look like? Let's draw our axes here. So x-axis, y-axis. And we know that this function just kind of sort of looks like that, okay, parabola. Okay. So this is y equals x squared. Okay. So let's zoom in just a little bit here. Right, and we know there is a local min right here at x equals 0, right? It's also a global min, but the second derivative test doesn't really help us out with global mins and maxes. We don't really care about that. So anyway, that's simple example part 1. It might not seem that simple, but it's just because we're going through all the details here. But there's really not much happening. Okay, we just take the first derivative, find the critical points, just like we did for the first derivative test. Nothing new there. But what's new now is we take a second derivative, and then we evaluate the second derivative at the critical point, which in this case is x equals 0. Okay, so that's the only thing that's different. And then once we do that, we go to these cases here, and we see, was the second derivative positive, was it negative, or was it 0? And it turned out that the second derivative was positive, so we ended up with this case here. Okay, so that's a specific example of that happening. So let's do part B, which is fairly similar but a little bit different. Okay, so we'll erase this. So part B, same instructions for all the parts in this example. Just find where the local extrema occur. And again, if you want to find out what the actual extreme value is, just take your x value and plug it back into the original function. But we're not so concerned with that because that's all the same as what we did before. So now our function is going to be g of x equals 4 minus 3x squared. Okay, so just like before, we're going to take the first derivative and use that to find the critical points. So g prime of x equals, derivative of 4 is 0, then we have minus 3x squared, so that derivative is negative 6x. Okay. And to find the critical points, we want to know where is the 0, where is it undefined? Well, it's a polynomial, so it's never undefined, but it's going to be 0 when negative 6x equals 0, and that happens when x equals 0. Okay. So again, just like before, actually, we have a critical point at x equals 0. So now, this, so far, it's all the same as the first derivative test, right? It's all the same, but now what's different from the first derivative test is now we're going to take the second derivative. So what's g double prime? G double prime of x equals, well, the second derivative is just the derivative of the first derivative. So negative 6x, the derivative of that is negative 6. Okay. So now what the second derivative test tells us is, okay, so we've used this part here. Now we have to evaluate the second derivative at c, which in this case is 0. C, here's our c value, x equals 0. So we want to see, is f double prime to c, or in this case the function is g, but it doesn't matter what you call the function. The principles are all the same. So is the second derivative positive? Is it negative, or is it 0? So what we want to do then is evaluate, let's stop using the blue here, g double prime to 0. Well, just like in part A, the second derivative is a constant, it's always negative 6. So g double prime to 0 is negative 6. Okay. So no matter what x is, g double prime of x is always negative 6. And this is less than 0. So that corresponds to this part here. Okay, the second derivative is negative, so that tells us the original function has a local max at x equals c, and in our case c is 0. So the second derivative test tells us that the original function f of x has a local max at x equals 0. So again, this is our c value we used here. So we just did the second derivative test with 0 as our c value. Okay. And if we were to graph this, what would that look like? Well, 4 minus 3x squared, so it's pretty much just a parabola turned upside down, stretched a little bit, and then pushed up 4. So let's make some room and graph that. So just again, f of x is a local max at x equals 0. So we can toss that into a graphing calculator real quick, or if you remember from your pre-calculus days how to graph things like that, which if you don't remember, that's totally fine. There's actually more thorough methods in calculus that we'll talk about soon. So 4 minus 3x squared, so that's parabola turned upside down, stretched in a little bit, and pushed up 4 units. So that's going to look kind of sort of something like this. Just a rough sketch, could be a lot better. Ugh. Okay. So this is y equals g of x here, or y equals 4 minus 3x squared. So right here at x equals 0, we have a local max right here. Okay, and that's I erased it, but that's what we found out from the second derivative test, the local max here. Okay, so those are 2 simple examples. There's still more coming up in this video, but that's so we did a simple example with this case and a simple example with this case. Now let's talk about what could happen with this third case here. So as we already mentioned a few times, if f double prime to c is 0, we just don't know what's going to happen. We could have a min, we could have a max, we could have neither. So let's see some examples of that. So we'll do that here. Let's erase this. Okay, so part C, let's say we have h of x equals x cubed. All right, so we're going to do the second derivative test. So the first thing we do is find all the critical points. So h prime of x equals 3x squared. Okay, and if we want to find critical points, we find out where's the first derivative 0, where is it undefined. It's a polynomial, so it's never undefined, so we just take it and set it equal to 0. 3x squared equals 0. Now if 3x squared equals 0, then what's the only thing x could be? Just 0. Okay? So, these examples are a little bit simplistic, but, we just want to use simple examples, not so simple that nothing is happening, but also simple enough that we can easily illustrate these concepts here and sort of see what's happening here. Okay, so x equals 0, that's our critical point. The only critical point we have here. So now, just like in parts A and B, we're going to take the second derivative, h double prime of x, which in this case is 6x. Okay? And then what we want to do is evaluate the second derivative at the critical point. So h double prime of 0. Okay, so when you do the second derivative test, this is sort of the key step here, is you want to evaluate the second derivative at the critical point. Then you want to know, is it positive, is it negative, or hopefully not, is it 0? So h double prime to 0 equals 6 times 0, which is 0. Okay. And that's bad, right? That's bad because now we're, in this case here, so f, or in this case h, doesn't matter what we call the function, the second derivative at the critical point is 0. So that means we have to try something else. And specifically, we would try the first derivative test. And I'm not going to go through it because it's not part of this video, but if we do the first derivative test here, then what we're going to find is that there's actually no extrema here. So it's still a critical point by definition, right, because the first derivative is 0 there, but there's no local min, there's no local max. And x cubed is a pretty simple function, so we know if we graph that, it just kind of sort of looks like this. Okay. So this is y equals x cubed here. All right, and I mean, it's a pretty bad rough sketch, but there is a horizontal tangent line that goes right through here where x equals 0. Okay, because we know that there is this critical point here, and h prime of x is 0. Okay, h prime of x is 0 when x is 0. So we do have a horizontal tangent line here. But it's not a local min and it's not a local max, right? So that's an example of this third case where you don't have a min or a max. Now, like we mentioned before, you could have this case, or sorry, excuse me, you could have a min or you could have a max, even if f double prime to c is 0. So let's see some examples of that. Okay, so just to recap real quick, we did an example where we ended up with a positive second derivative and it was indeed a local min. That's what the second derivative test tells us. We had an example, part B, where the second derivative was negative, which means local max. And we just did in part C an example where the second derivative is 0, and we saw that what we had was no min and no max. So now let's do part D. And part D is f of x equals 2x to the fourth. Okay. So same instructions, find where the local extrema occur. Now for 2x to the fourth, f primed of x is going to be 8x to the third. Okay. And again, we want to find all the critical points. Okay, so find the critical points, and that means where's the derivative 0, where is it undefined? But it's a polynomial, so it's never undefined, so we just want to know where's the 0. So 8x cubed equals 0. So that's only going to happen if x is 0, right? That only happens if x is 0. So just like all the other examples so far, our only critical point is x equals 0. So now we go to the second derivative, okay, f double prime of x. and that's going to be 24x squared. Okay, 24x squared. Now we want to know, now the second derivative, the next step in the second derivative test is evaluate the second derivative at this critical point x equals 0. So f double prime to 0 equals 24 times 0 squared. 0 squared is 0, 0 times 24 is 0, so this is just 0. Okay. So here we are again in this case here. If f double prime to c is 0, then we need to try something else. But what do we actually have here? So, you know, what we could do is do the first derivative test, and again, we won't go through it just in the interest of time, and it's not really the main point of the video. But 2x to the fourth, what does that look like? Well, if we toss that in a graphing calculator, or you know, if we just know x to the fourth and then stretch it a little bit, basically it's going to kind of look like x squared, but squished in a little. So it's got that sort of parabola shape to it, but not exactly. It's just kind of stretched and squished in. Pretty bad sketch, but you know. So here's our critical point at x equals 0. You know, we do have that horizontal tangent line there. And this actually is a local minimum, right? Okay, so what we just saw was an example of this third case here where we actually have a local min. So far we've seen the third case where we had neither, and a third case where we've had a local min. Okay, so right away we can already tell that, you know, if f double prime to c is 0, if we do the second derivative test and we end up with this case, we just don't know what we can say. You know, there might be a local min, there might be, you know, neither a min nor a max, and then now we're going to do part E, where you know, you're probably going to be able to guess what's going to happen, but we're going to end up with a max. Okay? And we just want to go through it just to be thorough and show that really anything could happen if the second derivative is 0. And I think after part E, we're going to summarize and recap what the steps are for the second derivative test. Okay, so part E. So we'll do part E, then we'll recap the steps real quick. Okay, so part E, our function is g of x equals 2 minus 5x to the fourth. Okay. So first step, you know, find all our critical points. So g prime of x equals, so if we take a derivative, derivative 2 is just 0, then minus 5x to the fourth, that derivative is going to be minus 20x cubed. Okay. So again, critical point, so that means where's the derivative 0, where is it undefined? But it's a polynomial, so it's never undefined, but also, since we're going to use the second derivative test, we don't care where it's undefined, because we're not allowed to have that for the second derivative test anyway. It's just, you know, totally irrelevant for this specific example, but it's worth pointing out because you should always be thinking about it if you want to effectively use the second derivative test. So take this guy, set it equal to 0 to find the critical points we could use. So negative 20x cubed equals 0. That's only going to happen if x is 0. Only happens if x is 0. Just like all the other examples we looked at. And again, we'll do more complicated examples later. But anyway, so the next thing we want to do is find the second derivative. So g double prime of x equals negative 60 x squared. Okay. Now we evaluate the second derivative at this critical point 0. Okay. And it's going to be negative 60 times 0 squared. But 0 squared is 0. 0 times any number, any real number is going to be 0, so this is just 0. So again, we're in this third case here where the second derivative at the critical point is 0. And we're going to have to try something else, which again could just be the first derivative test. And again, we won't do it here. But you know, what if we graph this? What does it look like? So if we were to graph that, it's going to kind of sort of look something like this. So x-axis, y-axis, 2 minus 5x to the fourth. So if we take x to the fourth, which pretty much has a shape like x squared, but squished in a little bit, kind of stretched, pulled up. So x to the fourth, reflect over the x-axis, this 5 is just going to stretch it out even more and then push it up 2 units. So it's really just kind of sort of something like this. Kind of, again, a pretty bad rough sketch, but you know, it doesn't matter for the purposes of what we're doing. So here at x equals 0, you know, here's our critical point, right? We have a horizontal tangent line here. And this is y equals g of x. Or excuse me, sorry, that's our tangent line. This is y equals g of x here. Sorry about that. Okay. So, and what do we have here? That's actually a local max, right? So this is an example where the second derivative is 0, but you have a local max. So to summarize, we've seen, well, let's summarize everything real quick. We've seen this case where f double prime to c is positive, and we end up with a local min there, right? Because that's what the second derivative test tells us we're going to have. We had this case where f double prime to c is negative, which gave us a local max. And then we just saw 3 examples of this case where the second derivative is 0. And we had one example where there was neither a min nor a max, one example with a min, and one example with a max. So again, I just want to point out that, you know, if you do this and you get the second derivative equals 0, you got to be careful because you just can't conclude anything. You could have a min, you could have a max, you could have neither. You'll have to try something else, which usually means try the first derivative test. But anyway, so that's mostly it for this video. Let's, since we didn't really outline the steps, let's go ahead and do that now. So we'll outline what all the steps are when we do the second derivative test. Okay, so we talked a lot about what the second derivative test is and why it works, but now let's outline the steps for how to use it. So step one is going to be find, you know, you can find the critical points, but really when you do the second derivative test, you always have the restriction that f prime to c must exist. Okay, so you know you're only going to care about where is the first derivative 0. But just to be thorough, you know, find all the critical points. So find all the critical points, which I'll abbreviate CP of f of x. Okay, and the reason, you know, why do we want to look for all the critical points if we can only use the ones where the first derivative exists? Because if you're just looking for mins and maxes, you know, you want to find all the critical points, and if you have critical points where the first derivative doesn't exist, you won't be able to use the second derivative test. You'll have to use the first derivative test, but you know, it's good to know, you know, when you look for mins and maxes, you should always find all the critical points anyway. So if you have some critical points where the first derivative doesn't exist, yeah, you won't be able to use the second derivative test, but at least you'll know those critical points are there so that you can use something else. Now I also want to point out that for some applications it might not actually matter, and we'll do those a little bit later on. But for now, just, you know, find all the critical points of f of x. Always the safest thing to do there. And then step 2, we want to take the critical points where the first derivative exists. Or well, actually, well, step 2. Okay, step 2 is going to be find f double prime of x. Okay, so step 1, find all the critical points. When you do step 1, you're going to end up taking the first derivative. So step 2, find the second derivative. You just take the derivative of the derivative. So step 2 might not be too bad, but depending on the function, it could actually be pretty bad. And we'll see some more complicated examples later on. Okay, and then step 3 is going to be evaluate f double prime of c at each critical point, which let's abbreviate CP. I guess we're not really saving much time now. At each critical point C, where f prime to c exists. Okay, because again, if you have a critical point C, then remember, critical point might be the case that f prime to c does not exist. But again, from the second derivative test, we only care about critical points where the first derivative exists. Or sorry, we don't, I shouldn't say we only care about those, but we can only use those for the second derivative test. And again, we'll see some more complicated examples later on where we can't use those. And then step 4 really isn't a step, but once you evaluate f double prime to c, basically use these 3 cases here to see which case we have. So step 1, find all the critical points. Step 2, find the second derivative. Step 3, evaluate the second derivative at each critical point C where f prime to c exists. Okay, because remember that was one of our restrictions here. And then step 4, if f double prime to c exists. Okay, because that's also a restriction, right? F double prime to c must also exist. So, you know, it might be the case that the first derivative exists, but the second derivative doesn't. You could have a weird function where that happens. It probably won't happen too often, but just, you know that it could happen. But if the second derivative also exists, then go to these cases here. Then see which case we have. And see which case we have. Okay, and what that means is, you know, is the second derivative positive? And if it is, then we have a local min. Is the second derivative negative? If it is, then we have a local max. Is the second derivative 0? Hopefully not, but if it is, then we have to do something else, which usually means the first derivative test. Okay, so kind of lengthy video there, but we just wanted to introduce the second derivative test, talk about what it is, kind of why it works, do some simple examples, and then here's a recap / summary of the steps we want to do. So we'll refer back to these steps in the next few videos when we do these more complicated examples. And that's an intro to the second derivative test.